Welcome, everyone. Thank you for being here today and for joining us. I'm Gina Henry. I'm the Associate Dean for Advancement for the College of Engineering. And I'd like to welcome everyone and thank you again for joining us. We may have a few people who are still going to be joining us in the minutes to come, but we'll go ahead and get started. In July of this year, the College of Engineering kicked off a new webinar series titled Faculty Insights, a 20-minute briefing. This webinar is the third session in that series. In this virtual series, faculty from across the College of Engineering will share insights into their research and its impact, and will provide perspective for us for the future. Following each 20-minute presentation, attendees will have the opportunity to direct questions and comments to our speaker. Our featured speaker today is Vanessa Chen. She is an assistant professor of electrical and computer engineering here at Carnegie Mellon University. Vanessa received her PhD in electrical and computer engineering from CMU in 2013. Before joining CMU, she was an assistant professor at The Ohio State University, and prior to that, she was with Qualcomm working on intelligent data acquisition systems for mobile devices. From 2010 to 2013 at Carnegie Mellon, she focused her research on self-healing systems and high-speed data conversion interfaces. And she also held a research internship position at IBM T.J. Watson Research Center in 2012. Vanessa's work has appeared in top academic conferences and has been featured as highlights in the IEEE International Solid State Circuits Conference. She was the recipient of the NSF Career Award in 2019, the Analog Devices Outstanding Student Designer Award in 2013, and the IBM PhD Fellowship in 2012. Her research interests focus on hardware algorithm co-design for machine learning, security, and neural interfaces. Today, Vanessa will be talking to us about real-time learning and countering of security threats in smart transportation and the Internet of Things systems. Vanessa, thank you for being here today to share your research and insights with us. Before I turn things over to Vanessa, please remember to submit any questions that you might have via the Q&A feature at the bottom of your screen. Mara Kudrick, who is the Director of Development for the College of Engineering, will be moderating the question and answer session with Vanessa at the conclusion of this presentation. With that, I'll turn it over to Vanessa.
Hello, everyone. Thank you, Gina, for the nice introduction. I hope you all have a great Thanksgiving weekend. And today I would like to talk about the real-time learning and countering of security threats for smart transportation and IoT systems. This is the outline for today's talk. First, I will introduce the background and motivations of our designs for wireless devices. Then I will go through 3 research projects that we are working on, including in-sensor encryption, or signature augmentation, and the on-chip threat detection module. And finally, I will summarize our findings and the research and the future works. So our world is rapidly moving toward a wireless future where everything will be connected through the internet. Such evolving development in interconnectivities between electrical devices are leading toward faster information sharing, which in turn will facilitate a number of societal benefits from social connectivity to economic development. And the data generated from the pervasive interface could enable big data analysis to discover some technology that has not yet discovered yet. So the data generated from pervasive sensor interface would be collected for the massive data analysis, and that would include health condition and some sensitive private information. And for such a data and spectrum sharing platform, security would be a central aspect of the rapidly increasing connected technology that are currently being developed for the future. So while research in security approaches have traditionally focused on digital and software domain, at present, hardware design for security is still a largely unexplored area in RF to terahertz microelectronics and electromagnetics. And RF security is particularly important for electronic devices that are seeing a dramatic increase in sensing capability. For example, the health monitoring devices and electromagnetic sensors such as radar and imaging system. So as devices capabilities are improved, this development also open potential pathways for exploitation by malicious actors. And each sensing or communication connection a device makes with external world is a potentially vulnerable access point, and the security of such systems need to be addressed. So furthermore, the pervasive wireless charging raises another security concern. Most devices still require recharging as the power domain is shared with the charger, which could reveal the data processing activities, especially when the electronic devices and vehicles are under use and also receiving wireless charging from the third-party provider. So for the era of smart transportation and IoT, the large volume of data related to critical financial and personal health, control, and privacy information are transmitted. The secure wireless microelectronics would be a key enabler to ensure safety and trustworthy communication system. So this slide shows the attacker model of IoT system. The first one is that the information could be leaked through intercepting the signal in main channel if no encryption or the password is applied, which is common in the health monitoring devices. And also the data patterns can be decoded from side channel analysis. For example, in the power domain, if the encryption module generates observable patterns. And the second threat model is that an attacker can transmit phase signal to the electromagnetic sensors to take control of the autonomy system as long as the attacking signal is at the receiving edge range. So the third threat model associated with our security is the Trojan problem, which is likely to be inserted into the IC during the design phase or the fabrication process. So hardware Trojan could cause phase agent, alter the functionality and computational results, or to be used as a killer switch that can be triggered by the attacker. Therefore, physical layer security must be considered in future technologies for both personal and commercial information protection, and particularly with advancing development in autonomy and IoT technologies. So this slide shows the conventional security measure. So as you can see, digital and software security approaches are well investigated for securing information on devices after the signal is converted into the digital domain. For example, PUF, crypto engine, and frequency hopping can be carried out in the digital domain. However, if we look at the sensor front-end circuit, you would typically have an amplifier, data converter, and a wireless transceiver. So due to different RF anode characteristics, digital measures may have limited capabilities when applied to the RF front-end and anode domain. So if the attacker target at the anode domain, they could easily reverse the design, collect the sensitive information, and cause performance degradation, or they can send malicious signals to control the system. And to achieve the goal of short response time, we are trying to explore intrinsic device characteristics such as nonlinearity, memory effect, and mismatch to develop security approaches in the RF anode domain and provide end-to-end protection for the whole system. So here we have, I will be going to introduce our in-sensor encryption. So this slide shows the proposed health monitoring system. And to continuously monitor the health conditions, sensors or body network need to be always on. And wireless sensors are powered by small battery or through energy harvesting, which creates a critical constraint for energy consumption. And development of such ultra-low power encryption engine can prevent information leakage because only cipher messages will be transmitted. And in this design, we developed the machine learning classifier here to extract the meaningful information first. And the classification result would then be scrambled and permutated through the reconfigurable KLT encryption engine before the signal is transmitted. And in this way, only cipher messages will be sent to the aggregator, so the transmission energy can be highly decreased to enable continuous monitoring. And because the harvested energy may not be stable, we are trying to develop a circuit that can work under low power supply voltages. So to efficiently encrypt the signal at sensor front end, we are exploring the time domain circuit to carry out the machine learning classification function and also the KLT encryption. So KLT encryption can essentially be thought of as deterministic noise, which is a periodic and noise-like in time domain, and it's continuous and wideband in frequency domain. So with matched KLT generators embedded in both sensors and the receiver, and the transmitter, the signal can be encrypted and decrypted in real time. And KLT encryption can be performed before transmission via the edge node to produce a transform waveform that is unintelligible. And dynamics of the discrete KLT system can be governed by nonlinear maps like this. So as you can see, the dynamic signal evolves from an initial condition and follows self-similarity principles at different scale. So different orbits can be generated from different initial conditions, and the transmitter and the receiver would just need to be synchronized with the same initial condition. So here we realize the piecewise linear map with the switch capacitor topology that can work under 0.5 volt to scramble and permeate the sample signal in the loop. So to make the system more dynamic, because this is very low power, multiple maps can be cascaded to increase the overall gain. And to avoid using power-hungry closed-loop amplifier, multiple stage architecture using reconfigurable open-loop amplifier are explored to increase the overall gain. And to reduce the reconfiguration overhead, combinatorial randomness from the minimum size devices are deployed to provide maximum programmability. So different subsets like this will be enabled for different devices, which enable physically unclonable function to ensure complete security measure. And the transformation function can be updated from time to time with different selected subsets so that the signal can travel in time-varying orbit to strengthen the security. And when signal propagate to the next stage, the next transformation function, the first map can be reconfigured with the selection of the combinatorial subset to ensure that the overall gain flow, the overall gain could follow the dynamic load without interrupting its operation. So we have designed the KLT circuits in 65 nanometer CMOS technology. As you can see that the state space trajectory shows high sensitivity to the initial conditions. Hence, different deterministic noise can be created with different initial inputs. And the initial state and targeting map can be set up through synchronization to ensure that two KLT systems have the same trajectories. And here the output signal appear to have the chaotic behavior with zero cross correlation and impulse-like autocorrelation, which also meet NIST standard for a true random code generator. And we tested the side channel emission with correlated power analysis, and it doesn't show intelligible patterns on the power supply, which means it's robust to side channel attack. And the figure illustrates unsuccessful correlation power analysis on the proposed chaotic system with 50K traces. And the result demonstrate that the approach can counter side channel attack, and also it can efficiently encrypt the signals under very low power supply. So so this is the in-sensor encryption. And for the second project, we focus on developing the rapid RF signal identification module to be embedded into radars for self-driving cars or drones. And it can also be used to detect authorized users for accessing multifunction RF devices, such as the mini cells. And recent studies have demonstrated that the ability to wirelessly hack into modern vehicles, and particularly the self-navigation system, need to send detection signal to collect information from the surroundings. And this kind of system may be under malicious attack when the sense signal have been modified. Such vulnerability to hacking or exploitation can have significant consequences for people's safety. As they are high motion vehicles, the detection and response time need to be as short as possible. Also, they are battery operated, so we need a low power identification module to rapidly identify the authorized signal and suppress the malicious attacks. And signal noise and interference in a dense RF environment may affect the accuracy of classification on raw samples. And in a crowded spectrum, it may require a long processing time to extract the features for discriminating subtle difference between the desired signal and the adversary signal. So to enable efficient and robust identification, we explore augmented nonlinearity and memory effect in power amplifier. So based on the generating model here, the algorithm will create modulated signal to drive the power amplifier for creating patterns that exhibit specific signatures. And then the neural network will perform probability inference with posterior distribution inferred by Bayesian observers generating model. And the features and internal state can be updated and synchronized to create time-varying signatures. And in this way, the inherent nonlinear function in power amplifier can be exploited as unique RF signatures through variational autoencoder to enhance system trustworthiness. So here we developed a Class E power amplifier. So this power amplifier is designed to achieve high power efficiency and broadcast its unique signatures. And the design process focuses on generating desired time domain behavior of the drain voltage waveform when while lowering the matrix network loss, and also reduce the voltage across the power amplifier transistor to achieve good power efficiency. And this power amplifier transistor was sized in accordance to the power losses associated with the non-zero transistor on resistance. And the nonlinearity and memory effect can be programmed through the combinatorial drivers here. And the pattern is controlled by VAE to choose a combination from selectable units in the pre-driver. So we have tapped out the design last month, and the design is very compact that fits in a 1 by 1 millimeter square area in 65 nanometer. And in January, we'll be receiving the prototype from TSMC. So in such a system, the generating model of the PA would act as a decoder, which would identify the data signature introduced by the nonlinearity and memory effect of the PA. And we implemented the machine learning classifier in FPGA to assess its classification performance. So this slide shows the single layer of the Bayesian neural network architecture. And the weight matrix is reshaped in a format where the weight on the column can be assessed in parallel to participate in the multiplication with the input element. So the inputs and weights are optimized for memory access bandwidth to perform matrix operation. And only one input would need to be accessed in one cycle. That could reduce the access bandwidth on the input memory. And the output accumulator would be preloaded with the biases of the layer. And the neural network is pipelined by layers to achieve better throughput. So for a signal with 50 dBc adjacent channel power rejection, our preliminary simulation indicate that the accuracy is higher than 99%. And with the prototype coming back in January next year, we will carry out our experiments on the real world environment. And in such type of communication architecture, our fingerprinting and identification can effectively enhance the communication security. So in this slide, I'm going to introduce our third project. And this project is to develop non-invasive sensing and threat detection system that can be integrated on chip through post-processing. And since most circuit behavior can be observed in the power domain, through collecting and analyzing the electromagnetic emission from the power line, we will be able to understand if there's any Trojan failure or malicious signal insertion in the chip. So here we collaborate with Professor Jimmy Zhu to develop on-chip magnetic tunnel-based sensors for instant power, current, and electromagnetic emission monitoring. And on top of this power line, the low power and low voltage on-chip sensor will be developed to sense small changes of magnetic field and inform the machine learning circuit in the backend. And this figure shows that there's a fast guiding layer on top of the interconnect. It can amplify the changes of the electromagnetic field. And the impedance of the spin toward devices here will vary with the sense strength of the magnetic field. And this narrow scale heterostructure can be integrated with CMOS technology to develop high fidelity sensors. And we plan to embed this into the interconnect to build on-chip power grid monitoring to build the on-chip power grid monitoring circuit. So here we will be developing a bridge sensing circuit to achieve high accuracy resistance measurement of these EM sensors while eliminating any response to the external field disturbance. And in order to rapidly predict and detect the potential threat, this machine learning circuit will be pre-trained to learn the normal behavior of the system with different operation schemes. So the building detection system could enable the prediction of a variety of adversaries in real time. And since we already have the spin-torque oscillator, for the machine learning module, we integrate the spin-torque oscillator with the DNA. So, so here it's the single wireless neuron. So one wireless neuron consists of an STO and a DNA here. So the figure shows the integrating and firing mechanism based on magnetically tuned spin oscillator and a thermally activated DNA. And embedding in the DNA is a microwave absorption unit that can absorb the microwave in a very narrow frequency range. So it could be modeled as a bandpass filter for this DNA. And under this condition, if the neuron at this layer emits a signal within the absorption range, the neuron at the next layer would absorb the microwave and heat up. So the temperature rise changes the length of the DNA and the distance between the magnetic particle and the STO. So according to how much energy and microwave absorption unit has integrated, the oscillator will decide to fire or not. So, if a cell, So if a cell generates a resonant frequency that is outside of the microwave absorption range of the DNA, no energy will be absorbed by the DNA, and the FM particle is far away from the local STO, and then that will stop the spin-torque oscillator from oscillating. So the position of the magnetic particle and the bias of the STO would determine the frequency distribution. So this wireless neuron can be applied to design the weights and the architecture of Bayesian neural network to perform variational inference. So this slide shows the structure of a wireless Bayesian neural networks, and each neuron absorbs wireless signals from neurons at previous layer, performs the signal transformation, and generates the wireless signal to activate neurons at the next layer. And because the integration are distance dependent and physically changing the magnetic particle separation distance would alter the spin-torque oscillation frequency and the energy absorbed by the neuron in the next layer. So the simulated power consumption for 200 oscillators operating at 20 gigahertz is 625 microwatt, and that can enable efficient computing. And then, so when the threat is detected, the suppression mechanism will be activated to mitigate the damage immediately. So to wrap up my talk, my research focuses on developing RF security that can be coupled with the digital counterpart to provide an end-to-end multi-layer solution for the storage, processing, and transmission of ultra-sensitive data, and to shorten the response time while achieving good energy efficiency. We explore useful device primitives to perform chaotic encryption for energy harvesting sensors. And we developed the variational autoencoder based RF signature augmentation and identification technology for automotive radar and network vehicles. And furthermore, the emerging materials with unique wireless properties are developed to develop the real-time learning and countering measures. So the need for research in the RF anode security is expanding at an accelerated rate. And in addition to current ubiquitous sensing and computing technology, future IoT devices will be built using heterogeneous integration that could potentially expand new attack surfaces. And in the heterogeneous integration, many chips will be integrated together to enhance powerful functionalities. However, one chip could radiate RF signal or direct heat to corrupt other chips, and it could also have near-range monitoring capability to extract valuable information like encryption keys, or it could trigger power shunt corruption, disabling the entire device. So a robust security measure is required to be integrated in the RF front end. And there's also a need for near zero near zero power and lightweight authentication module for IoT devices. For example, the ultra efficient true random code generator and the strong perf where the process and temperature variation and aging effect can be compensated. And these all primitives would make up the first line of defense for low power devices. And then through the intelligent integration of the various primitives, strong countermeasure can be developed. And lastly, we envision that the novel hardware security approach through co-design of microelectronic systems with algorithm and cyber physical standards can achieve and enable better performance and security measure to strengthen trustworthy IoT and smart transportation systems. So that's all I have today. And thank you. Any question?
Vanessa, thank you for that fantastic and very, very interesting presentation. I'd like to ask everyone to submit your questions at this time, and we will start out with the question. What's the detection efficacy of the wireless sensing approach?
Yeah, so you mean would that be the last one for the sensor or the radar?
He didn't specify, so maybe the last one.
I see. Yeah, so we haven't really implemented on a device yet, so it's based on the device model we have now. So we use it to observe a device that has the power consumption at milliwatt range. So because the changes of the EM field would affect the detection range. So you can see that in this slide. We have an amplification layer here to amplify the electromagnetic field generated by the power line here. So we believe if the power is larger, then the sensitivity will be higher.
Okay, I don't see any other questions at this time. Okay, here we go. Class of 1980, just a comment just saying that it's fascinating that these measures can be implemented with very little power consumption.
Yeah, we are working on that. Yeah.
Vanessa, has it been hard for you to conduct your research in this remote environment, or has it been pretty seamless?
Yeah, it's a bit hard. Yeah, without face-to-face discussion, it's a bit hard to work on this. And especially for some projects, we need to perform experiments. And but students are quite fantastic. So they will be able to do it remotely. Yeah.
That's great. Okay. Before we wrap up, any last questions for Vanessa? Okay, well, I think we'll pass it back to Gina, and thank you, Vanessa, for your time today.
Okay, thank you.
Thank you, Mara, for moderating that question and answer session. And thank you, Vanessa, so much for the very thought-provoking and informative program. I would also like to thank everyone in the audience for participating and joining us today. I hope you'll be able to join us at one of our future Faculty Insights programs. So please keep an eye out for a follow-up email soon. That email will include a link to the recording from this session. And watch your email too for the announcement of the next session, which will be after the new year. So I hope everyone has a good holiday season, a wonderful new year. I hope we see you before then, but thanks again for joining us and have a great day.
Thank you so much. Bye-bye.